Okay, so we want to talk about clipping of the common collector or buffer amplifier. So here is our basic amplifier. You see our input is connected into the base and our output is connected onto the collector, and so this should be a nice buffer. So we're going to run this. You see that we put in a 5-volt signal. It's centered around 10 volts, so it's going up to 15 and down to about 5 volts. And it's not clipping right now. Everything looks nice and sinusoidal until we connect in our load. So if we connect in our load, let's zoom in on these a little bit. Okay, so what we see here is we're clipping down here. So is this saturation or cutoff? So first of all, let's see. So saturation is the voltage across the transistor. So at this point, the highest voltage this gets is right here, which is like 13 volts. So we have about 7 volts across the transistor, and then it goes down from there. So it's definitely not saturation. So in cutoff, we want to look at the current. So in order to measure the current, we're going to put a resistor in here. We're going to make it a small value. So let's just pick 1 micro ohm, which is basically 0. And then we're going to look at the current going down. So you see the arrows pointing down. So at some point, so at this point here, you see, oh, nanoamp, so it's cut off. So this has no current going down. So this point is, so this flat part here is when it goes into cutoff. But you see, it's interesting. It cuts off in current, but it doesn't cut off in voltage because we got plenty of voltage here, but the current wears out. So what we're going to need to do is we're going to need to analyze what's going on in the transistor. So let's look at this in more detail. So we're going to copy this over so that we can look at it in greater detail. Okay, so what we're doing is that we're interested in the current going down here. And you see that the current is going to split into a piece of current that goes down here and a piece of current that goes right there, because we're basically just treating the capacitor as a short. Okay, and then this total current here is going to be the sum of these two currents. So let's look at these two currents by starting by looking at the voltages. So I'm looking at the voltage right here. So this is biased, so it is going to go from a voltage of 15 volts down to a voltage of 5 volts, and you see it's just sinusoidally looking like that. Well, if we look at the current, let's just call this I sub E. So the I sub E is going to be equal to the VE divided by RE. So you can kind of see that this is going to go, okay, and then let's look at the voltage at this point. So the voltage at this point, this is DC biased or DC blocked. So that looks like that. And then this here is V sub E, and we're going to call this V sub L. And then the I sub L is just going to be the VL divided by the R load. Okay, so we want to look at 2 points. So we're going to look at this point right here. So at this point right here, I of 1 is going to be equal to, now we're just going to sum the two together. So we have VE over, well, let's just put in the 15. So 15 over RE plus the 5 over the RL, and that's greater than 0. Everything's great. So, but now we want to look at this point right here. Which we'll call point 2. So I at point 2 is going to be equal to, the one through the emitter went down to 5 volts, so that's 5 over RE. And the one in the load is equal to a minus 5 over R sub L. So you see that this is equal to 5 minus 5 RL, and we need this greater than 0. So what we see is that I have to make RE less than RL so that I have enough current bias to go through. So let's go back to our design. And so this is 100 ohms, so we're just going to make this 70 ohms. And then we have to rebias it. So we're going to rebias it to 10 volts, and so dot step param R will go 10K to 1000K and 10K steps. Okay, and then we run this, and we're looking for the voltage right here. We want it to be 10 volts, so we come over here. 10 volts is right around 16. We better sweep in a little better. So let's go 10 to 20. Okay, that's a little smoother. So we go to 10, and so 15.6K. And we're at 10 volts. Okay, so now we are going to change this to our transient. So if we run this, we see that there's no clipping here, even if we're going about 5 volts. If I look at the signal right here, you see we're only going down to, we're getting down to 27 milliamps, so we have plenty of room. The interesting thing here is you see we had to set the DC bias point at like 140 milliamps to get this to work. So it has to have a very high bias current for it to work. But it works, and we are done.